Now, in this video, I am going to explain some important substances of group 15, that is the nitrogen family. And this, the first is nitrogen or dinitrogen. And so, it has the formula N2. Dinitrogen means two atoms are present together. Now, first we'll see the laboratory preparation, how it is prepared in laboratory. So, first method is by heating ammonium dichromate. Now, ammonium dichromate, it is able to produce pure nitrogen. Ammonium dichromate solid on heating. So, this ammonium dichromate solid. It on heating not at very high temperature but at moderate temperature. It is around 250 degrees Celsius, something like that. And so it gives rise to pure nitrogen gas is given. Pure nitrogen gas is given. So this is the almost in pure form plus chromium trioxide solid and plus water vapors are fluid. So this is very important method for the laboratory purpose. In a small quantity we can prepare nitrogen for the experimental purposes. Now second method is by reaction between ammonium nitrate. Ammonium nitrate solution can be taken. Now in this method, in place of ammonium nitrate, there can be ammonium chloride or any such compounds have to be taken. This can be easily decomposed by the heating. So we can have the sodium nitrite and ammonium chloride solution. So there are different methods, but here we are going through the laboratory method. So this ammonium chloride NH4Cl aqueous plus NaNO2 aqueous. Now this on heating strongly, there is the reaction and there is the nitrogen gas and plus NaCl plus H2O, this aqueous. So this is there. There are several methods to prepare any compound. Now next is by heating azides. Azides are common name for nitrites. Azides or nitrites in dry state. When we heat barium nitride or heavy metal nitrides, barium nitride or calcium nitride, this solid on heating, barium nitride or this calcium nitride. Now this solid and we have to heat strongly, and so as a result there is formation of nitrogen gas plus barium solid is produced. So this is very important method. That this method is to get the pure nitrogen. So this is there also different methods to prepare. Now we'll see next about the properties. Now coming to the properties. So as you know, it is a colorless. It is colorless. It has no color. Colorless, odorless, tasteless gas. no color, no smell, no taste. It is there. And it is highly inert. It is highly inert gas. And it is due to very strong bond. There is the triple bond between the nitrogen. So the energy required to break the molecule is very high. So the dissociation enthalpy is very high, and so it is highly inert gas, and as a result it has many uses in different applications, and it is very little soluble in water also. Very little soluble also, approximately 23.2 cc in water at 273 Kelvin, means at 0 degrees Celsius. Its solubility is very less. Anything is less soluble because there is no force of attraction between the molecule and the solvent. So this is the reason. As it is inert, it cannot combine with the water or any solvent and a result. So it is less soluble, and so you can imagine at 0 degree Celsius. But this nitrogen, it is active, or it becomes active at high temperature. So it becomes active at elevated. Elevated means high temperature. Elevated or high temperature means it is inert at room temperature. You all know the branded biscuits, potato chips, etc. Snacks, they are packed in nitrogen. They are flushed with nitrogen gas because this nitrogen prevents from reactivity as it is inert. So it becomes active at elevated or high temperature and forms different compounds. It forms different compounds. That's here. If you take any metal, so they create with metals also compounds by reaction with metals and non-metals both. Non-metals both. See how this magnesium reacts with nitrogen. Magnesium solid. Magnesium is reactive metal, and magnesium reacts with nitrogen, and there is formation of magnesium nitride. So this is magnesium nitride or magnesium azide. Similarly, it reacts with hydrogen also. Reacts with hydrogen. By which process? By Haber's process, and at 760 atmosphere, then to this temperature and 200 atmosphere pressure, iron as catalyst and molybdenum as promoter. Iron as catalyst and molybdenum as promoter. This in the ratio of 1:3. And there is formation of ammonia gas, and here we have the equation. So this is what? This is nothing but this is Haber's process. This is Haber's process to prepare ammonia by taking hydrogen and nitrogen ratio of 1:3 at approximately 760 Kelvin temperature, 200 atmosphere pressure, and iron as catalyst and molybdenum as promoter. Iron as catalyst and this iron as catalyst, molybdenum as promoter. So this is there, and so this is about some of the important properties. Now we'll see some more. Nitrogen, it is very inert, but it combines at different metals and non-metals, and like it combines in internal combustion engines, internal combustion engines. Internal combustion engine means like diesel engines, engines of the vehicles, four-wheelers, high energy vehicles. Oxygen is taken for the combustion, and so it combines with oxygen. So nitrogen gas, it combines with oxygen. Nitrogen gas, it combines with oxygen. Very high temperature, around 2000 Kelvin, and there formation of nitric oxide gas. And this is present from air, and so this is it. Then the last we'll see the usage of nitrogen. Now we are in the last segment of the nitrogen. So nitrogen, it is very much important in different conditions. So first is in preserving biological materials. Biological materials like sements of the animals. Sements of the animals, they are preserved in liquid nitrogen at very, very low temperature. So like sements of animals are preserved at very low temperature. In animal husbandry, or the persons who want to preserve their identity, their semens are preserved, and in case of any emergency it can be used for the future generations. Then in metallurgical operations like processing of metals, the place where metals are processed, if there is oxygen, if there is any gas, it may react with a very molten metal. So the acute place where the metals are processed, actually they are given with inert atmosphere. How? By providing an atmosphere of nitrogen. So temperature is not so there because low temperature is very high when the metals are molten, and so it is there. Then in cryosurgery means surgery at low temperature. The surgeries which are highly complex, surgery of heart, surgery of brain, and so there is a very delicacy requirement. So the veins are highly thin, and so there is the blood loss. So that is used by the surgeons, and that is called as cryosurgery. Then in preparation of different substances, like urea. Urea is fertilizer. Then ammonia just by Haber's process. Then nitrites, etc. So there are countless uses, and so there are some important uses of nitrogen or dyed nitrogen. Now next is ammonia, NH3. So again we see the first preparation. So first, we have to see the lab method. So, in laboratories, it is prepared by reaction between ammonium salts with alkali. Ammonium salts and alkali. So, like we take the ammonium sulfate aqueous plus NaOH aqueous. So, when they are heated strongly, their solutions are heated strongly. So, there is formation of ammonia gas plus there is Na2SO4 plus there is H2O. So, this is the simplest way to prepare ammonia in the laboratory. Now, other same, like we take any other salt, take the case of ammonium chloride, and similarly alkali, let the calcium hydroxide. So again there is the formation of NH3 gas, then there is calcium chloride plus H2O. So these are the laboratory methods to prepare. These are the lab methods. Now in nature, what can I say? Nature. How ammonia comes in nature? Actually, all the animals, they consume proteins, and the proteins, they are converted into different nitrogenous compounds, and ultimately there is formation of urea in the body of all the animals. So urea, NH2, CO, NH2. This aqueous solution, uric acid is converted into urea, and this on heating, it gives rise to ammonium carbonate, and it again gives rise to ammonia plus CO2 plus H2O. So this is there to have the preparation. But on larger scale, how it is prepared? It is prepared by Haber's process. Now third is commercial method. So on large scale or commercially, it is prepared by Haber's process. And in Haber's process, nitrogen gas and hydrogen gas, it is taken in the ratio of 1:3, and there are some ambient conditions here, approximately 706 Kelvin temperature, around 200 atmospheric pressure. Iron is catalyst and molybdenum is promoter. This is catalyst. This molybdenum, it is promoter. It starts the reaction, so it is the starter. The role of molybdenum just to initiate the reaction. It helps in the chain initiating reaction, and so there is formation of ammonia, and as a result we have this. So this is the ratio of 1:3. So this is the commercial method to prepare. These are the ambient conditions, around 760 Kelvin temperature, 200 atmospheric pressure, and iron catalyst, molybdenum as promoter. So this is about the preparation. Now we'll see the properties of ammonia. Now coming to the properties of ammonia, so you all know it is a colorless gas and having pungent smell. So it is colorless. It has no color. Colorless, pungent smelling. Pungent smelling means it irritates our nose. It irritates our respiratory system. Pungent smelling highly, highly soluble, highly soluble in water. You know, it is highly soluble in water. Another term, it is having basic character. It is quite soluble in water. And so, like this, NH3 plus H2O. There is summation of NH4OH. And this NH4OH, you know, it is unstable and it gives rise to NH4 aqueous plus OH minus. As a result, its solution is basic. It is less basic, not it is strongly basic in nature. Now it's you know, it's melting and boiling points. Melting and boiling points are quite low. Melting points and boiling points are quite low because it can be easily liquefied. It is quickly liquefiable gas. Now the melting point is 198.4 Kelvin and 239.7. These are the very low conditions. So this is their brief introduction. Now it reacts with different metal compounds. It reacts with metal compounds to form colored salts, and it can be used to identify. It can be used to identify the presence of some ions or cation. See how? If you take copper sulfate aqueous, and add here this NH3, and so there is the formation of, in place of this, we may take ammonium hydroxide, both can be taken, and so there is formation of a complex. This is deep blue color. So this principle is used in the conformation of the copper ions. Copper ions simply, this is there. This is tetra amine copper second sulfate. This is the coordinate compound. This is the complex compound. So what we can say? Ammonia is a good complexing substance. Ammonia is good complexing ligand. We will see about ligands later on. Similarly, this can be used in case of salts of any other metal, like we take the case of ferric chloride aqueous. It has light orange color, and when we add NH3 or ammonium hydroxide, there is formation of brown colored complex, and this hydroxide, here we may take NH4OH. This is brown colored precipitate. This is the identification. Similarly, many more. The particular color indicates the presence of that ion. So similarly, when we take the iron, so the brown colored precipitate indicates. But in few places, the color is discharged. Like we take the PPT white, white PPT of silver chloride. White PPT of silver chloride. Then when we add, ammonium hydroxide. Ammonium hydroxide is added. And as a result, there is the formation of, colorless precipitate. Colorless precipitate is formed. In place of this, you may take ammonia because as it is insoluble in form of white precipitate, so there is formation of here again complex. As I have said, there is formation of complex, and this is colorless compound. This is colorless compound. Now this principle is used. This principle is used in the conformation of chlorine chloride ion. Then when we test the presence of chlorides, what happens? We add some substance to get the white PPT, and then we add ammonia, excess of ammonia. Then this, it is dissolved. It is dissolved, and so we can see this how it is obtained. If you take any compound, like take the case of CaCl2, and then we add some silver nitrate. So there is formation of AgCl white, and there is CaNO3. So this is aqueous. So this is the point we confirm the presence of. So this white PPT, it is white PPT, white precipitate. So this is very important to know. Now we know about the usage of ammonia. Now we are in the last segment of this video, and it is the usage of ammonia. So first now it is used as a refrigerant. Used as refrigerant for manufacture of ice. Then it is used in the cold storage where the fruits, vegetables, they are kept at low temperature. So this is the refrigerant. Again, why? Because ammonia can be compressed easily. It is highly liquefiable. It is easily liquefiable gas because of its very low melting and very low boiling point. So it can be very easily compressed by the compressor. Then in preparation of different salts of ammonia. Different salts of ammonia can be prepared. Different salts of ammonia can be prepared. Then in preparation of different fertilizers like ammonium sulfate, then ammonium nitrate. These are the fertilizers for the plants. And so then in detection of different metal ions. Different metals ions, just you have seen, different metal ions can be detected by the formation of precipitate.